Welcome to ICDD's InSession webinars. Anja Dosen, ICDD's Senior Scientific Editor, will present clay analysis. Please remember to visit icdd.com for information on future free webinars, educational events, product information, and to purchase PDF databases and JADE software.
So clays have been used as building materials for centuries, and they're components of ceramics like porcelains and tiles. Clays are also used in production of plastic, paints, papers, polymers, cosmetics, and so on. So they have been linked with the origin of life, actually. So they have been linked with the prebiotic synthesis of biomolecules. Also, clays are ubiquitous on Earth, and their existence has been also confirmed on Mars. So really any place that had some kind of weathering or hydrothermal alteration will have presence of clays. Applications of clays are numerous. They are eco-friendly and cost-effective materials. They are used in wastewater treatment, remediation of pollutants. They can be used in photocatalysis. They're used for nanomaterials and nanocomposites, and as I mentioned, in ceramic industry to produce different types of porcelain, ceramics, electroceramics, and so on. Also, clays are used in biomedical fields and pharmaceutical fields as active ingredients or excipients for drug delivery and tissue engineering, and have been used for medicinal purposes since ancient times. So what is the difference between clays and clay minerals? Clay is the bulk material. Clay is naturally occurring material that's composed of fine-grained minerals. It is primarily composed of a small group of minerals that are called clay minerals. Clay is plastic at an appropriate water content, and it gets hardened once dried or fired. Clay science is a really broad scientific field that includes different types of clay mineral research that can be fundamental for clay structure analysis and surface properties analysis, and also can go to industrial and environmental applications. So clays are generally disordered materials. Here is just an example of some X-ray diffraction patterns, so you can see the difference. We have two nicely ordered, well-crystallized materials, different particle size. We have this garnet with really nice sharp peaks, or this anatase that is nanometric, so it has these wider peaks, but as you can see, all the peaks are well defined. Whereas when we look at this clay, we can see right away that there is disorder present, that peaks are asymmetric, and this diffraction pattern looks very different from the other two. So how do we analyze clay? I'm going to be talking about it. And I want to point out that our PDF 5+ database contains what we call a clay subfile. It is within the mineral subfile, and we can use this to help us with our clay analysis, where we have different clay mineral patterns that we can use as references. So in this case, what I'm showing you is our experimental clay entries, entries that have raw diffraction data. This is what I've selected here to show. And what is a great thing is that you can display your raw diffraction data in your search window along with the mineral name, which can greatly help with your analysis if you're just starting by visually comparing your analysis with these entries. The fact that we can display a mineral name here as well is really useful, because we can see right away what is the difference between these. For example, this one is glycolated and oriented. This one has been heated. This hasn't been untreated. This hasn't been treated. and so on, instead of just looking at the compound name, which is the same in all of these cases. So let's talk a little bit about clay minerals and what they are. Clay minerals are phyllosilicate minerals. They're layered silicates that consist of tetrahedral and octahedral sheets. These sheets are stacked together. Tetrahedral sheets consist of silica and alumina tetrahedra, and octahedral sheets, these right here, they contain divalent or trivalent cation that is bonded with these oxygens, which helps achieve neutrality of these sheets. So these are the two main sheets of clay minerals. Now, depending on the stacking of these sheets, we can have TO or 1-to-1 clay structures, or 2-to-1 or TOT clay structures. So what is a TO? Is a tetrahedral, octahedral. So these are sequences of tetrahedral and octahedral sheets stacked together. And then if we have 2-to-1, which is 2 tetrahedral and 1 octahedral sheets, we have octahedral sheets that are sandwiched between 2 tetrahedral sheets. And here is an example. Here we have an example of a 1-to-1 layer. See tetrahedral and octahedral sheets. 2-to-1 layer, we have tetrahedral, then octahedral, and then tetrahedral sheets. So these here are interlayer spacings that are usually filled with some cations, or what we call interlayered cations, or hydrated interlayer cations. And in this case, you can see that this interlayer spacing is wider when we have hydrated cations than here when there is no water present. Now let's talk a little bit about the octahedral sheets. Depending on the type of cation that exists in octahedral sheets, clay can be dioctahedral or trioctahedral. Dioctahedral clays have 2 trivalent cations in the octahedral sheets. Trioctahedral clays have 3 divalent cations in octahedral sheets. In any case, these add up to 6 to neutralize the charge. And so we have dioctahedral and trioctahedral clays. So all of this type of bonding and stacking dictates the platy habit, the sheet stacking dictates the platy habit of clay minerals. Clay layers are bound together with these interlayer cations, or a sheet of hydroxides. So these are bound with hydrogen bonds or ionic bonds that are much weaker than the covalent bonds that we have within the layers themselves. And clay minerals are rarely pure. Generally, we have a mix type of clay mineral. However, if we have like an end members or pure clays, they have identical stacking of layers, and the sequence is repeated identically. However, once this sequence is interrupted with some other type of layer, we end up with an interlayered material, and we observe it as an intermediate type of material. Here is an example of montmorillonite clay, where we see here a randomly oriented clay sample and heated and oriented clay sample. So if we have an oriented clay sample, that means that we have a strong preferred orientation and we're observing the basal reflections, whereas when we have a random sample, we can observe all reflections, and these will tell us different things about different types of disorder in clay minerals. Now a little bit about different types of clay minerals. I'm not going to go over all of them, just going to mention some. So kaolinite is a dioctahedral 1-to-1 clay mineral. There are 4 types of minerals in this group: kaolinite, dicite, nacrite, and halloysite. and there is no substitutions between them. They are non-expandable, and kaolinite can be found everywhere in soils, in permeable bedrock, in warm regions, and it is formed as a weathering product or from hydrothermal alteration of feldspars, for example. Tri-octahedral 1-to-1 clays as an example is serpentine group. There are 3 different minerals in this group, and they differ based on their topology. So we have lizardite, which shows an ideal layer topology, and then we have antigarite, which has this modulated structure, this wave type of morphology, and chrysotile, which is bent. It shows this cylindrical morphology. And here's a TM that's very, very interesting looking. 2-to-1 clay minerals, that is a larger group of minerals. They can be both expandable and non-expandable. So we have a pyrophyllite pyrophyllite talc group that is a non-expandable. Micas also non-expandable. Vermiculites and smectites that are expandable clays, and chlorites are non-expandable. All of these clay minerals are they exist in a broad range of conditions. Chlorites and micas occur in all types of rock, including different metamorphic conditions. We'll be talking about illite and smectites and their interlayering sequence. So illite is a 2-to-1 clay mineral. It is mica-like, and it is an umbrella term. It is not one specific mineral. It is an umbrella term that covers a wide variety of chemical compositions, and it is most commonly found in sedimentary rocks and soils. Smectites, on the other hand, are found also in sedimentary rocks and soils, but they are expandable minerals and can be both dioctahedral and trioctahedral. So an interesting thing about smectites is that their interlayer spacing can both expand and contract without damaging the structure. So it usually contains some water, just if the minerals are on the surface from humidity, and can also facilitate organic molecules. So once water or polar or organic molecules are found in this interlayer space, the smectite interlayer space expands. If we dry it or heat it up, we can squeeze this out, and the interlayer space is going to contract, but the structure is not going to be damaged. These platy habits and sheets of clays can be stacked in different ways. We can and joined in different ways, and all of that is can create different types of disorder in clay minerals. So mixed layering or interstratification or interlayering is a very common type of disorder in clay minerals, where we have layers of different clay minerals that are stacked together and act as a coherent scattering unit. So and this term mixed layer identifies 2 or more clay structures that are vertically stacked parallel to the c-axis. This interstratification can be ordered if we have some kind of ordered sequence, or it can be random or partially ordered or disordered if the sequence is not set. So how does that work? We have a fundamental particle that's a building block of a clay sequence, and that is a 1 nanometer or 10 angstrom particle that can be also considered as an illite layer sheet. And here we have these particles that are stacked together, joined with some interlayer cations, and this here is a stacking of of these 10 angstrom particles. Now, if we have a hydrated sheet of cations, we're going to have a little larger despacing and a little larger interlayer spacing. So this would be 14 or 15 angstrom. So this would be this could be a smectite, and these would be the second type of layer. Let's call it layer B. That would be stacked B on top of B layers. So now if we have a regular interstratification sequence, we're going to have an AB type sequence, and we're going to see these two particles together scattering as a coherent scattering unit. Also, this sequence can be random, and these layers can be stacked in a completely random fashion, but they're still going to be acting as a coherent scattering unit. So we have developed some ways of seeing if we have an interlayered material or not, or minerals or not. So as I mentioned, the illite smectite sequence is most commonly observed. This sequence serves as an index for thermal maturity of sedimentary basins and sedimentary rocks like black shales, for example, which I'll show this example later in the talk. And it provides some information regarding the low-grade metamorphism, where temperatures weren't high enough to destroy these structures. Illite is more stable at higher temperatures and pressures, so the amount of illite increases with depth and temperature. And this involves the transformation of smectite to illite. It is a solid state transformation that occurs when there is pressure or heat added into the system, like overburden pressure, for example. During this process, water or organic matter that's trapped in smectite inner layers gets released. Another type of disorder in clays are different polytypes. So polytypism, clay mineral polytypes form due to a systematic disorder, that is the layer stacking disorder. In this case, I'm showing you two types of illite 1M and illite 2M1. So in illite 1M, we have sheets that are stacked stacked on top of each other. However, there's a translation, they're offset, and that type of stacking is creating this type of X-ray diffraction pattern. Whereas illite 2M1 has a rotational disorder. So the sheets are rotated in regards to each other, and that will create a different type of X-ray diffraction pattern. So what we want to when we want to determine different polytypes, we try and analyze randomly oriented clay samples in order to try and determine these. So how do we know all this? If we think of clay, what do we think of some reddish or light color material that is essentially looks the same. It is difficult to determine how many different phases, and especially how many different types of clay minerals we have in the bulk sample. So our main tool in determining clay polytypes is X-ray diffraction and different types of disorder. So with X-ray diffraction, we can observe phase shifts, disorder, and mixed layering. In general, X-ray diffraction is used for structural determination. So each phase or each mineral has its own distinct diffraction pattern. They're like fingerprints. So when we analyze our sample and we use a database like PDF5+, we can compare our raw data pattern with the phases we have in the database and determine which phase or phases we have in our sample. However, we can also that would be an example here. This is again annotates that I showed earlier. We would determine several of these peaks or all of them, and we would definitively know that we're looking at annotates. With X-ray diffraction, we can also observe structural disorder or interlayering. And we can also observe the existence of an amorphous phase, which I'm showing here in the case of this sample. So these little humps are what we call amorphous humps, meaning that the material is partially amorphous. So we want to know what is the difference between ordered and disordered samples. In ordered samples, peaks are well-defined. They are predicted by Bragg's law. We know exactly where they are, and we can easily determine them using the phase ID methods. In disordered samples, the arrangement of atoms is not necessarily known, and the X-ray diffraction pattern will show us an average structure, not a distinct structure. So that is the case of clays and some solid solutions. And in that case, peaks will deviate from the Bragg positions. Again, we're going back to our example. As you can see, this garnet has all peaks very well defined. Their positions are easily determined. If this sample were to be in some kind of mixture with other samples, it would still be fairly easy to determine what it is based on this PDF card. Or that we can actually overlay and make sure that we're seeing the exact peaks. Same thing for this annotase, although it is nanometric, it just has a smaller particle size, but it's still very well defined. Whereas we're showing this hydrohaloisite, which clearly has asymmetric peaks, very high background, and and it not as easily recognizable if it was in a mixture as these other two samples. When we analyze clays, we want to look at both oriented and random sample preparations. For that, we want to separate a less than 2 micron fraction, which is going to contain the most clays and is gonna that we're gonna avoid the influence of larger particle size minerals that could contaminate our analysis in our samples. So we need to do a very careful sample preparation because clays are, as we know, difficult to analyze, and we have to pay attention to the mixtures, layer swelling and contraction, and preferred orientation. So we have methods that are going to help us with all of these. Here is, so I'm going to move on to sample preparation. Just want to point out that again, clays are almost always multi-phase samples. They will contain some fractions of quartz, feldspars, and maybe some other minerals, although we're going to try to avoid having them in our samples. But since most samples that were, most natural mineral samples have been weathered and have gone through some erosion or hydrothermal alteration processes, these larger grains are getting they get reworked and become smaller and will enter or in a way contaminate our clay size fraction. So here is one of the classic methods of sample preparation. This is a way of separating less than 2 micron fraction using settling tubes method. So I'm explaining this starting with a soft rock. If you have a soil sample or a loose sample, you will skip this first step. But if we have a soft rock, like we don't want to we want to crush it to some small particle size, small enough that we can work with. So centimeter or less would be ideal. We could then put these little rock chunks in, for example, industrial grade blender, and grind a little bit in a suspension in water. So with the distilled water, so we can then use this fine fraction and work with it to separate the less than 2 micron fraction where our clay minerals are going to be. So that's gonna go through an ultrasonic treatment where we're going to disaggregate the clay particles. Then we want to transfer this into settling tubes that we're going to work with, and we need to introduce an anti-flocculation agent that's going to stop these clays from flocculating, and we need to let that equilibrate. After that is done, we're gonna shake the settling tubes up and wait for exactly 3 hours and 50 minutes before we can extract the clay size fraction, which is less than 2 micron fraction, from the top 5 centimeters of the settling tubes. This has been calculated based on the Stokes law and the settling times. So once we've done this, I'm going to show you a photo in the next slide, but what is the easiest thing to do is just to take some of this solution with clay fraction and put it on a slide and let it dry. And we're gonna end up having an oriented slide because clays are all going to lay flat on their basal planes. So this is the settling tube method. As you can see, some of these are lighter on the top, meaning that the coarser material is settling faster, and this is what we want. So we're going to use the top 5 centimeters to extract our clays. Here's a table that's showing mean settling times for different particle size diameter in microns. We could do this also by centrifugation. We can do filter with vacuum pump or a clay paste smear. This is all to prepare an oriented clay sample where we're going to see well-developed basal reflections. Things to avoid during the sample preparation is dry grinding, and that will change the particle size distribution. It would add coarser minerals to the finer fraction. We can add excess heat to our system, which we don't want to do, and also shear the clay mineral particles and create some additional problems. So how do we prepare a random clay sample? That is also an important step in clay mineral analysis. We need to look at randomly oriented clay samples and observe all the reflections. That helps us determine different polytypes and the type of clay. This can be a very challenging task as well, because clays want to have this preferred orientation, and we need to try to avoid it. So that can be done by spray drying, freeze drying. We can try sieving, then shaking the sample, and side loading, meaning trying to load it in a different way and disturb the sample enough so that it will take some form of random orientation. We can also use a frosted slide. That's an etched slide, a surface along which we would load the sample, and that would help prevent the preferred orientation. Here are some pre-treatment methods. If we need to remove the organic matter or carbonates, we will use hydrogen peroxide or acetic acid. Glycolation is an important step that helps us see if there are expandable clay present in our samples. And another thing is cation saturation. using sodium or calcium salt solutions. So when we analyze oriented clay samples, we want to observe the basal reflection. So we want to look at an air-dried sample that has been untreated, an ethylene glycol saturated sample, an air-dried sample that has been heated to 300 and 500 or 550 degrees. So we want to do this because different clay minerals are going to act differently in these, depending on the type of treatment. So, for example, alite will not change. This is the D-spacing, and we see that it remains the same. The spacing of 10 angstrom will remain the same. However, smectites are going to have a different D-spacing depending on the cation. And once we glycolate them, the spacing is going to get larger. So continuing to the different analysis with heated samples, the spacing is going to get smaller again, which is what I mentioned before. Smectites are expandable, but they can also contract. So kaolinite, on the other hand, will be destroyed above 300 degrees. So around 500 degrees, kaolinite structure is destroyed, and we won't be able to see an X-ray diffraction pattern. The material will be amorphous. Again, we have a randomly oriented slide and an oriented clay sample. So what do we want to do? When we analyze clay minerals, we want to compare everything. That's kind of like all of these different sample preparations. We want to analyze them with X-ray diffraction and then compare all of them. We're gonna have to use a database with clay structures that's gonna help us in sample in phase identification and determination, but we need to have all these sample preparations done and analysis. When we look at random clay powders, as I mentioned, we're going to look at the full 2 theta range and observe all different reflections. When we're looking at oriented clay slides, we want to look at these 3 ranges from 5 to 10, 16 to 19, or 15 to 20, and 25 to 30, and observe the behavior of these peaks. So now I'm going to show you 2 examples of a pure smectite. That is, these are clay mineral standards, Wyoming smectite, and I'm going to show you an interlayered sequence of alite and smectite. So smectite, air-dried and glycolated. We can see right away that there is a difference between these 2 diffraction patterns. Air-dried sample will expand once it is saturated with ethylene glycol. The spacing will expand and this peak will move. It will not move. Really, we're gonna do a different X-ray diffraction analysis, and we're going to see that this peak appears at a lower 2 theta angle, which means that it has a higher D-spacing. If you look at 2 other ranges, 2 other basal reflections, we see that there is a big shift between each one of them. This sharp peak here is not a clay peak, that's a quartz peak. As I mentioned, it is very difficult to get rid of all the quartz in clay samples. So this is, now you see that there is a clear shift between the peaks once when we have smectite layers that are expandable and are saturated with ethylene glycol, a large polar molecule, and these peaks will swell, and we're going to see a different shifted, let's say, diffraction pattern between glycolated air-dried samples. Here we're seeing now all different sample preparations and analysis of an alite smectite interlayered interstratified sequence. This is a standard that has 70% of alite and 30% of smectite. So we have an air-dried sample X-ray diffraction here, ethylene glycolated sample. Here is a diffraction pattern. We have 300 degrees heated sample, 500 degrees heated, and this is a random sample X-ray diffraction pattern here. First thing that we can note is this difference between air-dried and glycolated sample. You can see that this peak is kind of in the middle of the two. And once we glycolated, we can distinctly see two peaks. I'm going to show this again in more detail. We can distinctly see two peaks, and we can safely say that, okay, so this is a smectite peak. It has expanded, and now we see a lower 2 theta or a higher D. And this here is an illite peak, which is a non-expandable clay. It did not change. When we heat up the samples, they're not, the position of this basal peak, or this one here, is not really changing. And that is actually what we expected. What is interesting here is this little peak is a kaolinite peak, and kaolinite is generally present in most clay samples. And we can see once we heat up the sample to 500 degrees, this peak is gone. And as I mentioned, kaolinite structure is destroyed around 500. So this is why we can't see it here. Here is the randomly oriented sample. And what I want to point out here is that all of these sharper peaks like this, they are quartz peaks, feldspar peaks, and kaolinite peaks. So I've plotted them all together. I've used Jade, our software that works together with our PDF 5+ database for this phase identification. And what I did, I identified all the phases that were easily identified, like quartz, kaolinite, and feldspar. In this case would be orthoclase. And as you can see, all of these peaks, this here is a kaolinite peak. It is really well defined. There is no shift. The phases is clearly there. It's clearly kaolinite. This red peak here is a quartz peak. You can see this like pointy end here. That's quartz. It is very clearly defined. And then this here, for example, is an orthoclase or a feldspar peak. So we know that our X-ray diffraction pattern is good. We can always use quartz as some kind of natural internal standard. We can see if that peak is shifted. We'll know that there is something, maybe wrong with our sample prep, but this is not the case here. And I've plotted illite and smectite. So as you can see, neither one is explaining this raw diffraction pattern peak. And that is because this is an interlayered material. So here is a detailed graph of a glycolated and air-dried sample. Air-dried sample shows one peak, an intermediate phase, and once we glycolate it, this is this green diffraction pattern. We see that illite peak here is shifting towards the position for the basal reflection of illite, and the smectite peak is separate, and we can see that we are working with an interlayered sequence. So now let's talk about a real world example. As I mentioned, I'm going to go over a little bit about illite smectite diagenesis in black shales. So this here is a black shale outcrop. Black shales are very common sedimentary rocks. They're dark colored, very, very fine grained. So if you just look at black shale, it's going to be difficult to determine how many different minerals it contains or what it really contains, because it's so fine grained. However, we know that black shales contain quartz, feldspars, smectite, illite, chlorites, kaolinite, pyrite very commonly. And that is, that's a great starting point for any kind of research. So in this case, we were looking at the illite-smectite sequence in black shales. Illite is more stable under pressure and temperatures that are different from the ones on surface, and smectite facilitates organic matter in black shales in its interlayer spacings. Normally, black shales will contain some kind of illite-smectite interlayer sequence, and once the overburden pressure is applied on these rocks, once they're buried, and this is some kind of low-grade metamorphism, the temperatures will rise and pressures will rise as well, and the organic matter or any kind of fluids that are within the smectite layers will get squeezed out or flushed out, and they will migrate to a reservoir if there is a reservoir present, and along with this, there will be a smectite to illite transformation sequence. So here's an example of this black shale. Again, I've used our Jade software to do the phase ID. Jade is really great for phase identification and hole pattern fitting, and actually a lot of other things. So different types of analysis. So what I did is I just did a quick phase analysis here, and I've clearly determined right away that I have quartz peaks, which is to be expected, and zinc oxide peaks, which are not normally found really in black shales, but these are present because they have been added as an internal standard. So what I'm interested here is this low angle, these low 2 theta peaks, and then the rest of this diffraction pattern seemed more or less simple. However, once you zoom in, you see that there are 52 peaks to be resolved. So first, and what was most important for me is to look at this low 2 theta angle and look at these clay peaks. So now I've switched to our PDF 5+ database and the extension Sieve, which helped me look into and compare these small angle peaks, low angle peaks, sorry, with different phases. So what I did here, I knew, of course, that I have quartz and zinc oxide, and I've added an illite. And this illite is here in pink, and I can see that this illite describes this peak fairly well. So I just don't know if that is an illite peak or an illite-smectite interlayered sequence. And also there are these 2 other small peaks that need to be resolved. As I mentioned, the PDF subfile, clay subfile, contains experimental data sets that contain raw data, and also contains calculated X-ray diffraction patterns for clay minerals. Currently, we have over 300 clay mineral entries in our database, and this clay subfile continues to grow as we're trying to add more clay mineral entries in the experimental data set, and all different X-ray diffraction patterns using all these different types of sample preparation, so that we have a more complete database. So since I decided that I have this illite, or maybe an illite-smectite interlayered sequence, I wanted to use this raw data X-ray diffraction pattern to compare it with calculated ones, and I have added kaolinite and chlorite, in this case clinochlor. So we have a peak around here. So this is what I want to look at. This is what I was interested in, those 3 little peaks. So this is a chlorite peak, which matches fairly well with what I had on my diffraction pattern raw data analysis. This is an illite or an illite smectite interlayered sequence, and here is the kaolinite peak, which matches really well because this one also has a little kaolinite impurity. So back to my sample, what I had to do now is compare air-dried and glycolated samples. And in my case, in the case of Dunkirk shale, there is no shift. This here is a chloride peak, which we don't expect to see any kind of shift because it's a non-expandable clay, but this was analyzed to see if this is an interlayered sequence, illite smectite, and there is no shift. So here is another basal reflection and another one. So none of them have shown the presence of smectite. So now back to jade and a whole pattern fitting quantitative phase analysis, which I was able to do now. And this is a really great thing that jade can do. It can incorporate clays in your quantitative phase analysis, which is generally a very challenging thing. So now that I knew that there are no smectites, I used illite, kaolinite, and chlorite to account for my clay minerals, and I added in this case albite, pyrite, and there is probably a little bit of zirconium, which was pretty hard to fit. I got 10.5% of zincite, and that is great because I know that I put in 10%. So I can tell that this was a good quantitative analysis, and I can safely say that I have about 27% of illite and no smectites in my sample. So what does this tell us? It tells us that the illite smectite diagenesis has been completed, and that can be validated also by a lack or a very small amount of potassium-bearing feldspar, which is normally used up during this diagenesis. Another example are K-bentonites. So K-bentonites are very thin clay layers that were deposits of volcanic ash. So we know that volcanic eruptions last hours or maybe minutes or days, but then they won't really deposit that much ash. But volcanic ash is deposited in what is a geologic instant. It's like a split second. So they're very thin layers that get deposited on a fairly large surface, and we can use those to determine different geologic time boundaries. What happens is that once volcanic glass is deposited and if it's in an alkaline environment, it will form smectite. There will be a transformation to smectite. So then, of course, we are going to have we're going to start a sequence of an illite smectite diagenesis that happens by an addition of environmental potassium that starts this diagenesis. And we have this conversion is, as I mentioned, associated with burial pressures or low-grade metamorphism or hydrothermal activity, geothermal activity. This generally starts at fairly low temperature. So here we want to look at different illite polytypes. In this case, we have an illite polytype 2M1, which we call the tetrahedral or an added illite. This is illite that has been added through weathering of the surrounded rock, and it is usually in a coarser size fraction, but now this is clay, so coarser size fraction is still less than 2 micron, but in this case it's between 0.2 and 2 microns, whereas diagenetic illite is going to be a 1M polytype, and that one is illite that was created by the diagenesis of smectite and transformation of smectite, and is generally going to be found in a less than 2 micron fraction. So for this, we have to go through extra steps of separating an even smaller size fraction. So a few more things now. We've talked a lot about illite and smectite, so a little bit about kaolinite. Kaolinitization is a process that is very useful for where we can get information about paleoclimate change. Kaolinite, as I mentioned, is a form of hydrothermal alterations and weathering processes from feldspars and micas. And it forms generally in warm and humid climates. So the rate of kaolinitization, how much it's being made, depends on temperatures, and it's very sensitive to climate change. If we're looking at different ratios of kaolinite and other minerals in sedimentary bases, we can get some information regarding the climate during the deposition of these basins. And distribution of kaolinite can tell us stuff about regional temperature changes. On the other hand, we have metakaolin. Metakaolin is what I mentioned, that the structure of kaolinite is being destroyed around 500 or 550 degrees. However, when we heat kaolinite, it will go through a process of hydroxylation, and as the hydroxyl groups are getting removed off the from the kaolin, the structure is going to collapse. However, it will look amorphous, but it will still retain some long-range ordering. This type of structure of kaolin structure is called metakaolin, and it has a very high surface area, and it is very reactive. And addition of this metakaolin to as a reinforcement in cement industry increases dramatically durability of concrete. Clays can be used as nanocomposite reinforcement as well. We have here some TM micrographs of intercalated and exfoliated clays. And if we adding just a little bit less than 5% or up to 5% of clay to a polymer matrix shows immensely improved properties of the polymer. And generally, clay polymer nanocomposite morphology is, we can have intercalated, which are clearly seen here at this TEM image, exfoliated, these are separate layer sheets, and tectoids. And I want to just mention about current research. I thought this was very interesting. This is a paper that has been published this year in American Mineralogist, and it is talking about microbially induced clay weathering. So this is microbially induced clay weathering is a process that occurs in anaerobic conditions generally, and it involves consumption of iron followed by a cation exchange. Bacterial metabolism in anaerobic conditions will use different cations as an energy source. So this will cause a transformation from smectite to illite and then to kaolinite. And this new paper that came out recently is proposing a new transformation that goes directly from smectite to kaolinite. They have observed the release of aluminum and silica from smectites via bacterial metabolism, and proposed this new model that occurs via the layer collapse. And the main characterization tools they used were X-ray diffraction and TEM. So what I wanted to point out here is that there are still so many different ways of interpretation and processes that need research. Just to mention again, our clay mineral subfile. the ICDD is sponsoring a project with Professor Stephen Hillier of the James Hutton Institute in Scotland, where we have this grant that is for submission of clay minerals for processing and inclusion into our database. As I mentioned, we are still inserting more minerals, and we plan to continue this as a long-term project. And in this, so the ICDD is leading the way of importing clay data and creating a unique and comprehensive collection of clay minerals data. And finally, in addition to jade, this is a clay tool that can be found in jade, and it is very useful in modeling a clay structure. So what I'm showing here is the sample that we've already looked at. This is our raw data, this purple line here, and the blue one is the model. As you can see here, I have chosen to say my primary clay or major clay is illite. I said a 10 angstrom illite. The minor clay is smectite. I said octahedral smectite with almost 13 angstrom despacing, and I said the probability of finding an illite is 70%, and I have modeled this peak not perfectly but fairly well. So this is a very useful tool for anyone who needs to model some clays and understand how these basal reflections are reacting and moving based on the addition of different cations, which you can change here, and different interlayering sequences. Lastly, resources. Two classic ones, Moore and Reynolds and Brindley and Brown. I prefer Moore and Reynolds. It is very hands-on. It is great. It has some great explanations about sample prep, clay interlayering, and understanding different processes. Brindley and Brown, classic book, also very useful. And I've added this handbook of clay science. There are 2 volumes in this set.